Hi everyone. In this video we're working on tangent lines, so we'll just jump right into it. When we talk about circles, a tangent line is a line that intersects the circle at only one point and is also going to be perpendicular to the radius at that point along the circle. And so this picture here is representative of a tangent line. So of course in blue, this is my circle. In purple, I'm showing you a radius of the circle. So it's just going a straight line from the center of the circle out to the circle itself here. This green line is representing the tangent line to the circle here. And the thing about a tangent line is that it's always perpendicular to the radius of the circle. Right there. So hopefully you can see this. And in Desmos, if you want to make this picture like I've made it, you know, the purpose of a tangent line is that you can actually, you know, you can see that it's intersecting the circle at one place, and actually just sort of around that point, that line is very, very close to the circle, but not quite touching it. So again, it only touches the circle in one place, and it's also perpendicular to the radius. So there's lots of tangent lines to a circle, but at any given point on the circle, there's only one. Okay, so when we talk about curves in general, so not just circles, but any kind of curve, the tangent line is the line that intersects the curve only once. And this is a really lazy definition, but for now, that's what I want you to think about. Is if you look at this right here, and we're talking about this red curve being my curve, and this blue line being the tangent line. This blue line is tangent to the red curve at this point here, and so you can see it's a little bit purple to show you where this tangent line is intersecting the curve. And I say it only intersects the curve once because right here it's not, you know, going through the curve twice, it's just barely touching it and bouncing off. But the astute among you may say, hey, over here it's also intersecting the curve a second time. And so I'm not being very precise whenever I say it intersects the curve only once. But I'm just trying to introduce you to the idea of a tangent line. And we're going to get more precise here in a moment, you know, later on in this video. So again, to give you maybe a better idea of a tangent line, I think it's nice to look at sort of an animation or maybe just a moving example. And Desmos is so good for this because it's so easy. But if I just drag this point, I can find the tangent line to this curve at any point. And maybe seeing this helps you get a better idea of what I mean by a tangent line. Okay, so at any point along this red curve, there's only one tangent line. There's lots of lines that are tangent to this curve, but at any point along the curve, there's only one. Now, to fully understand what we mean by tangent lines, and to give you that more rigorous or more formal definition, we first have to talk about what we call secant lines. And a secant line is going to be a line that passes through any 2 points along a curve. So in this example, I have a red curve and a blue secant line. So maybe I'll just label these. I know it's obvious already, but in blue, this is what I'm calling my secant line. And it's secant to the curve at these 2 points. So right here, it intersects the curve, and it also intersects again right here. And you may remember from algebra that any 2 points in the plane describes a line uniquely, right? So once I give you these 2 points and I tell you your line has to pass through these 2 points, well, then you could get out a ruler and line up your ruler along those 2 points, and you draw a line and there's no other line that passes through both of those points. This is what we mean by a secant line. And so let me label these 2 points. See if I can get both in the picture here. This first point, I'm going to label it x1, y1. So I'm using a subscript 1 to talk about my first point. And so in the picture that I've drawn, x1 is just the number 1. And then over here, y1 is just the number 3. So you know these are the x and the y values. And for the second point, this coordinate pair I'm going to label x2 comma y2, where it looks like x2 is just the number 2 and then y2 is just the number 4. So I'm giving a name to the coordinates of these 2 points that define where my secant line goes. Okay, now if I want to get the slope of the secant line, and we always use lowercase m to talk about the slope of a line, maybe, again, you remember from an earlier algebra class, that if you're given 2 points, the slope of a line passing through those points is going to be this. So the numerator I have y2 minus y1, and the denominator I have x2 minus x1. And when I was in algebra class, my teacher helped us to remember this by calling the slope rise over run. And so that y2 minus y1, that's what we mean by rise. It's a change in the vertical direction. And when we write x2 minus x1, that's the run. That's the change in the horizontal direction. By the way, if I haven't said this before, a lot of times we use a triangle like this to represent the Greek letter delta. And in math, when you see the Greek letter delta, this represents a change in something. So I might write this as the change in the vertical direction divided by the change in the horizontal direction for the same 2 points. And finally, just to maybe give you overkill on the number of different ways you can represent this, sometimes you see the slope set as delta y divided by delta x. But this is just shorthand for telling you the ratio of the change in the vertical direction to the change in the horizontal direction for a given 2 points. And so all of these, they really just mean the same thing. Now, because we chose points along my red curve, and if we say that my red curve describes a particular function, so let's say it describes the function f of x, then we would write to ourselves, we would say, well, the y-coordinate, y subscript 2, is just going to be our function evaluated at x subscript 2. And at the same time, y subscript 1 is just going to be the function evaluated at the input x subscript 1. And so then we can write the formula for the slope like this. So the numerator is now f evaluated at x2 minus f evaluated at x1 divided by x2 minus x1. So the difference in the function outputs divided by the difference in the function inputs for the same pair of points. Now what we're going to find is that for many different functions, whenever x2 and x1 become very close to each other, a lot of times those output values corresponding to those, so f of x2 and f of x1, also become very close. And this isn't true for all functions. You can think of functions where, they're a little bit pathological. You can think of some very misbehaved functions where this isn't the case. But for most of the functions we're dealing with in this class, whenever you have very similar inputs, you're also going to get very similar outputs of a function. And you'll notice that for any function, if we let the x values for those 2 points of our secant line be the same, so I set x2 equals x1, we're going to find that the slope of the secant line will be undefined. I'll let you think about why for just a second. Algebraically, if you're looking at this formula for the slope of the secant line, notice that in the denominator we're dividing by x2 minus x1. And so if these are the same value, that would make my denominator 0. And since we can't divide by 0, that leads to the slope being undefined. Geometrically speaking, if I let this x value be the same as this x value, and basically means this point moves to be the same point as the other one, really I'm not defining 2 points anymore, I'm just defining 1 point. And now 1 point does not uniquely define a line. In fact, for any given 1 point on your plane, you could actually draw infinitely many different lines through it, right? Because with just 1 point, you still have the freedom to choose the slope of the line. Hence, we can't really define a secant line with 1 point, we have to have 2 points to talk about a secant line. Okay, now we should be used to limits after last week's material. And so we're going to consider the following limit. We're going to take the limit as x2 approaches x1 of this expression, which you might remember, this might look familiar to you because this is the slope of the secant line. So we're taking the limit of the slope of the secant line as we let x2 approach x1. So we're saying we're going to let the x values of our function get very, very close to each other, but not exactly setting them equal to each other, right? So notice we're not setting x2 equal to x1 because we realized that that was undefined. And so we're not doing that, but what we are asking is, what's the slope of the secant line if we let these points get really, really close to each other? Also, before I move along, I want to define lowercase h. And we did this in the previous video too, so maybe this is a little bit of deja vu. But lowercase h for me means x2 minus x1. So this is the difference in the input values at our 2 points along the curve. And of course, if I choose to add x1 to both sides of this equation, we can also get this identity. But this really just follows from that previous definition of lowercase h, where we have x2 is equal to x1 plus h. And what I want to do now is I'm going to start with this limit and then make these two substitutions. So right here, that's what I mean by these substitutions. We can write this limit a little bit differently. So where I have x2 approaching x1, that's the same thing as saying the difference of x2 and x1 is going to 0. So that's the same thing as saying h is approaching 0. So now we can say we're taking the limit as h approaches 0. And then instead of x2 over here, we can write x1 plus h because of this definition. And in the denominator, instead of writing x2 minus x1, we can write h because of that definition. So hopefully you see how these two limits are actually the same thing after we define what we mean by lowercase h. So lowercase h is just the difference in the horizontal direction between x2 and x1. And now that we've sort of arrived here, using our mathematical intuition, we can finally define what we mean by the word tangent line. The tangent line to a curve at the point x is going to be the line that intersects the curve at the point x and has this slope. So in other words, the slope of the tangent line is going to be that limit. So the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now, we usually only use the word slope for lines, but if you want to stretch the definition of the word a little bit and generalize it, you might be able to say in kind of informal language that the tangent line to a curve at a point touches the curve at that point and has the same slope of the curve at that point. But again, you kind of have to extend the definition of slope to curves, if you know what I mean. So the steeper the curve is, the steeper the slope of the tangent line. And then one more definition here, but this isn't too much, I think. When we talk about the derivative of a function, so this is a new word here, but in calculus, one of the items that we study, one of the tools that we use is called the derivative, and the derivative of a function is going to be this. And notice I'm using this notation here. So if I write f prime of x, so in other words, if you see the little apostrophe between the f and the x in the function, when you read that f prime of x, this designates that we're talking about the derivative. So derivative. So if I were reading this out loud to you, I might say f prime of x is equal to this limit, or I might say that the derivative of f is this limit. But in any case, this is the definition of what we mean by the derivative. And you'll notice that this is actually the same limit, right? And so you might say that the derivative is the slope of the tangent line to the curve. Okay, so let's work some examples. Example 1 says, what is the formula for the line tangent to this particular function? So the function I give you says g of x equals square root x at the point x is equal to 4. So again, if I want the slope of the tangent line, the slope of the tangent line is just the derivative. And so what I'm going to write is g prime of x is equal to the limit as h approaches 0 of g evaluated at x plus h minus g of x divided by h. And this is going to give me the derivative if I evaluate this limit correctly. So remember, my g function is just the square root function. So this is going to be the limit as h approaches 0 of square root x plus h minus square root x divided by h. And what we can do here, it's going to take a little bit of algebra skills to untangle this. But what we can do is, sorry, give me a moment to rewrite this. We're going to multiply the top and the bottom of this fraction by the same expression. And so on the top, we're going to multiply by x plus h plus square root x. And on the bottom, let's multiply by the same thing. And what I'm multiplying by this new factor, since it's the same on top and bottom, it's the same thing as multiplying by 1. And you know that multiplying by 1 doesn't actually change the value of the expression, so we are good to go here. Now what we're doing in the numerator when we multiply across is a little bit tricky, and so I'll take it over here to the side, and I'm going to draw a little box to make sure I don't make any mistakes with my multiplication. And so what I have is square root of x plus h minus square root x times square root of x plus h plus square root x. So in this box in the top left, what I'm going to get is just x plus h. So the square roots will cancel when I multiply those. Over here, I'm going to have negative square root of x times x plus h. Over here, I'm going to have positive square root of x times x plus h. And then over here on this fourth box in the bottom right corner, I'm going to get negative x. So for my new numerator, I'm going to write the sum of these four boxes, which is going to be x plus h. And then notice that these diagonal boxes are going to cancel out because I've got the positive and the negative version of the same expression. And so I don't have to add those diagonal boxes. And then I'll write minus x. My new denominator, I'm going to multiply across to get h times square root of x plus h plus square root of x. Okay. Now let's take this limit as h goes to 0. So in other words, when I say take the limit, what I mean is now we have an expression here where I can actually, well, sorry, but maybe I'm jumping ahead of myself. Let me slow down and show you just one more step before I replace h with 0. Let me show you that in the numerator where I have x and minus x, that's going to cancel out and just give me h. And then in the denominator, we're still going to have h times square root x plus h plus h times square root x. Now, you'll notice that I have a factor of h in the numerator and a factor of h in both of the terms in the denominator. So actually, if I divide the top and bottom by h, I can cancel those guys out. And this is going to give me the limit, as h approaches 0, of 1 in the numerator, and then in the denominator, square root x plus h plus square root x. Okay. Now, if I set h equal to 0, in other words, taking the limit, what I have is 1 over square root x plus 0 plus square root x. This is 1 over 2 square root x in the denominator. And this is what we would call the derivative. So I can write g prime of x is equal to 1 divided by, and then in the denominator, 2 square root x. So we found the derivative of our function g. And yeah, I know it did take a lot of work and quite a bit of algebra, but it's good to practice with these limits. So if you see some practice problems in the back of your textbook, try to attack those and make sure you're pretty solid and feel good about your ability to evaluate limits. But we have not yet answered the question, because the question is, what is the formula for the line tangent to this function, or this curve, at the point x is equal to 4? And so we just found the slope of the tangent line at any given value of x, but now we want to know what is the slope specifically when x is equal to 4. So we'll evaluate the derivative, g prime of 4. And that's going to be 1 over 2 square root 4. The square root of 4 is just 2, so this is going to be 1 over 4. So what we found so far is that the slope of our tangent is actually going to be 1/4. That will be the slope of our tangent line. Notice that while we found the slope of the line, just knowing the slope doesn't tell you the full formula, but we can actually continue to find the rest of the line too. So I want to remind you, maybe if you've forgotten, that there is something called the point slope form of a line, and it's just an equation where we write y minus y naught equals m, which is the slope, times x minus x naught. So if you are actually given a point, a pair of coordinates x naught, y naught, and you're given a slope, you can actually use this formula to come up with the formula for your line. So now we actually know our slope of our tangent line, and we know the x-coordinate of our point. We want it to find it at x is equal to 4. But what is that y-coordinate? Well, so this would just be our function g evaluated at x naught. So this would be g of 4. And we haven't found this before yet, but the g function is just the square root function. So this is going to be square root of 4, which tells me that my y-coordinate is going to be 2. So here, the point where I want my line to intersect my curve is going to be 4, 2. And the slope of this line is again desired to be 1/4 for my slope. So now using this point slope form over here, I'm going to write y minus 2 is equal to 1/4 times x minus 4. And just to make this, just to rewrite it in a form that's explicit in terms of y, I'm going to add 2 to both sides and probably distribute that 1/4. And so this is going to be y equals 1/4 x minus 1 plus 2, so plus 1. And this is the slope-intercept form of our tangent line. So we did it. Let's check our answer using Desmos, just to make sure we didn't make any mistakes along the way. So our tangent line should be 1/4 x plus 1. Let's see how it is. Our original function, by the way, was the square root function, right? So if I write square root x, and I want to evaluate the tangent line, excuse me, I've got some extra junk on here. Let me get rid of that. If I want to evaluate the tangent line, or at least show you the tangent line, it's going to be 1/4 x plus 1. And I'll change that color so you can see it better. Changing it to a blue tangent line. You can see that this blue line intersects this red curve right at x is equal to 4. And otherwise it has the same slope, right? So just speaking very informally, the blue line has the same slope as this red curve right at that point x is equal to 4. So it looks like a tangent line. All right, and maybe this is a helpful visual that I kind of skipped over. But just to remind you that we were talking about how the tangent line is just the limit of the secant lines. Or I guess what I said before is that the slope of the tangent line is the limit of the slope of the secant line as these 2 points that are defining a secant line get closer and closer together. So right now, the way I have 2 separate points and a line passing through those points, that makes this line secant to the curve. But as I get these points closer and closer and closer together, the limit, as these points are getting extremely close to one another, is going to give me the tangent line here. So whenever points are relatively far apart on a curve, you can very easily tell that this is not a tangent line. But then whenever you get these 2 points that define a secant line, when you get them very, very close together, it starts to look exactly like your tangent line at that point. Again, that's the idea of a limit we covered before. Let's do another example, or maybe a few more examples before this video is over. Here it says example 2, what is the formula for the line tangent to this function? And you know what? I actually named this function h, but since we're using lowercase h to talk about a certain value when we go to evaluate the limit in the derivative, I'm going to change this to just good old f of x instead. So what is the formula for the line tangent to the curve, which is 1/x, at the point x is equal to 3? So same idea. If I want the slope of this tangent line, that means I'm going to be taking the derivative. So I will write the derivative here. F prime of x, remember the prime means derivative, is equal to the limit as h approaches 0 of f evaluated at x plus h minus f of x divided by h. Now, my f function is just the reciprocal function, 1 over x. And so actually plugging that in here, I get 1 over x plus h minus 1 over x in the numerator, and then h in the denominator. What I'm going to do in order to combine these fractions in the numerator is I'm going to multiply the left fraction by x over x, and then the right fraction by x plus h over x plus h. So I'm multiplying each fraction by the other's denominator. We're going to see how that turns out. So 1 over x plus h times x over x minus 1 over x times x plus h over x plus h. And so multiplying across, and I'm going to, I guess, take it over here. I never know how much room I'm going to need to evaluate these limits. So taking the limit as h approaches 0, again, multiplying across, this numerator is going to become x over x times x plus h, and then minus x plus h over the same denominator, x times x plus h. And now that those two have the same denominator, I can actually just subtract those and keep the denominator the same. So x minus x plus h. So x minus x is going to be 0, and 0 minus h is going to be negative h over x times x plus h. Now here I have a fraction in my numerator, and then, another h in this somewhat larger denominator down here. And so remember that if you divide by something, it's the same thing as multiplying times the reciprocal. Multiplying by the reciprocal. So let me show you what that would just look like if instead of dividing the whole thing by h, what if I just multiply times the reciprocal of h? Well, now you can see I have an h in my numerator and an h in my denominator, so we can get rid of those. And this simplifies it quite a bit to the limit as h is approaching 0 of negative 1 in the numerator over multiplying this denominator out, I get x squared plus hx. And at this point, I'm going to actually take that limit. So I'm going to set h equal to 0. And what you can see is I'm going to get negative 1 divided by x squared. And so this is the derivative. This is what we mean by f prime of x. We found that f prime of x is equal to negative 1 over x squared. And so if we want the slope of the tangent line at the point x is equal to 3, this slope is then going to be negative 1 over 3 squared, which is going to be negative 1/9. So it's a very shallow slope and just a slightly decreasing slope. Okay, we don't have the full formula for the tangent line yet. We just have the slope. But again, we're going to write out that the point slope form of a line. So we have y minus some initial value for y is equal to the slope we were given times x minus whatever our initial value is for x. So our initial value for x is 3. That's the point we want our tangent line to pass through. And remember that our y value associated here, I just have to use my f of x function, right? So remembering that the f function is just the reciprocal, that will be 1 over 3. So we have y minus 1/3 is equal to negative 1/9 times x minus 3. So then I have y minus 1/3, and I'll distribute that negative 1/9, so I get negative 1/9 x plus 1/3. And then I'm going to add 1/3 to both sides, and I find that the slope-intercept form of my tangent line should be y equals negative 1/9 x plus 2/3. And again, what we're going to do is use Desmos to check our answer and make sure that for the reciprocal function, the tangent line at x equals 3 is given by this right here. So for the reciprocal function 1 over x, I want the tangent line at x equals 3 to be negative 1 over 9 times x plus 2/3. And sure enough, when x is equal to 3, you can see that this blue line is tangent to this red curve. So we did our math correctly there. I do want to point out that derivatives do not always exist. And this is a typo that I'm going to correct really quick for you guys, where it says, what is the formula for the line? This is supposed to be the line tangent to the function absolute value x at the point x is equal to 0. So we're going to start by trying to find the slope of the tangent line. And you remember the slope of the tangent line is just the derivative. So I write f prime of x. And this is the limit as h approaches 0 of x plus h. And the f function is just the absolute value function. So I'll write absolute value x plus h minus absolute value of x divided by h. And since in the numerator we're just taking absolute values, this is going to be absolute value of h over h. And this particular function, we've graphed it before, and we've talked about this function before when you're doing limits, but for any positive values of h, the value of this expression is going to be positive 1. And for any negative values of h, it's going to be negative 1. And so the two-sided limit, doesn't exist here. Because if you were to take the right-sided limit, it would be positive 1. If you take the left-sided limit, it would be negative 1. And so this limit does not exist, which means that the derivative does not exist. The derivative here, at the point x is equal to 0 of our function absolute value of x, that derivative does not exist. And it's okay. I mean, there's lots of functions that have derivatives that do not exist at several points. To maybe give you an idea for why this is true, let me go back to Desmos and then just put on here the function absolute value of x. And it's a pretty simple function, but if you think about it, this derivative, or suppose we're trying to draw a tangent line at the point x equals 0. So I want a tangent line to this curve at the origin. Well, what if I just say y is equal to 0, right? So that blue line, it appears to be tangent to the curve, but I could also put y equals 1/2 x, and that also, it only intersects the curve at one point. And, if I make that negative 1/2 x, right? I mean, honestly, there's a lot of values for the slope, between negative 1 and positive 1, where this tangent line only ever intersects this, this red curve once. But that's my point, is that, the derivative is describing the slope of the tangent line. And really, this doesn't seem to actually be deterministic, right? So I can't specifically say that I have one derivative here. So anyways, we say the derivative does not exist because, again, of the limit idea. Whenever I take the limit, that limit doesn't exist. And hopefully you can also sort of intuitively tell that if I asked you right at the point x is equal to 0, what is the slope of the red curve? Well, it's very ambiguous. Just look at it. Okay. So derivatives don't always exist, and in fact, where a function is undefined, that's another point where a derivative doesn't exist. So if I give you the function that goes like x plus 1 divided by x minus 2, you see this is a rational function, and at x equals 2, the function is undefined because of that vertical asymptote. Well, you can be assured that the derivative does not exist here at x equals 2 either. If the function is undefined, the derivative doesn't exist. There are places, again, where the function is defined, like in this case, whenever I give the function absolute value of x. Clearly the function is defined for x equals 0, but there are places where the derivative doesn't exist, even when the function really is there. Just visually, any place where you don't have a derivative might seem to look a little bit pointy. So if you're doing your homework and maybe you get this question like this, and it asks you, for this graph right here, at what point does the derivative not exist? You might say, well, hey, that looks suspiciously pointy. So I think that this derivative does not exist when x is equal to -1, right? And again, the reason the derivative does not exist is because if someone asked you, hey, just loosely speaking, what's the slope of the curve at that point? You wouldn't really know what to say. You'd just say, oh, it's too pointy to tell. And so that's what we mean. Okay, example 4. Just like we approximate limits numerically, we can also approximate derivatives numerically. So this is going to be the last example of the video. But let's consider that whenever I take the derivative of this function f of x, we're talking about the limit as h approaches 0 of x plus h to the power 3.14159 minus x to the power 3.14159 divided by h. Now, if you want to try this out, please be my guest, and I'll honestly be very impressed if one of you guys can show me, but don't waste too much time on it. What I want to show you instead is that rather than, working quite so hard with our pencil and paper to write a closed form of this derivative, what I want to show you is that if we just skip ahead to worrying about what this limit reaches when I set x equal to 5, let's show that we can at least approximate this derivative using a calculator. So where x is equal to 5, this is going to be 5 plus h to the power 3.14159, and minus 5 to the power 3.14159 divided by h. And all it takes to approximate this numerically is just set, not h equal to 0, right? Because that would be undefined, but just set h equal to a really, really, really small number, like 0.000001. And whenever I take h to be 1/millionth like this, we can actually get a pretty good approximation of what this derivative is. So here we are, opening up Microsoft Excel because I don't have a calculator. Let me show you that for different values of h, we can calculate the derivative of this function at x equal 5. And let's start with the large values of h, just for kicks, and then on each row, we're going to take a smaller and smaller value of h. And I want to show you that this derivative is going to become more and more precise whenever we use smaller values of h to approximate the derivative. So my formula for the derivative, just to remind myself, it's going to be 5 plus h, 5 plus my value for h, to the power 3.14159 minus 5 to the power 3.141159 divided by h. And so if I use a width of h, right, which is, I mean, that's a very coarse approximation of the derivative, I get the value 121. And if I use 1/10 for h, I get 100, which is significantly different. And then going down to 100th, I get 99. And with each successive row, I'm shrinking down the value of h. And what I want you to be able to see here is that whenever the value of h gets small enough, you can actually tell that, like, the first 6 digits or so, they start to be the same thing. So I actually have a very high degree of confidence that the first 6 digits of accuracy of this particular derivative, when I evaluate it at x equals 5, is 98.6408. And after that, these approximations of the derivative are disagreeing. And I personally can't tell whether these are becoming more and more accurate or whether the very tiny value of h is messing with the round-off error that Excel uses as it's performing the calculation. Like, these are obviously bad, and that one's probably bad. But I always know that, you know, these first 6 digits are good. And so we were able to not get a exact answer using this route, but we were able to get an approximate answer, which is really good for most real-life applications as you go about applying it in engineering or business or whatever you need a derivative for. All right, thanks, and I guess I'll see you guys in the next video.